Next, detection of deadlock. Okay, so how do we detect deadlock? So allow the system to enter in deadlock state. Okay, detection algorithm, and then recovery scheme. Okay, let's have a single instance for each resource type. So maintain wait for graph. Okay, so nodes are processes. Okay, PI, next is PJ. If PI is waiting for PJ. Okay, so build a wait for graph and periodically look for cycles to find the circular wait condition. Okay, so the wait for graph contains nodes corresponding to process, as mentioned here, directed edges corresponding to resource held by one process and desired by the other. Okay, so let's get the resource allocation graph or the wait graph here. Okay, so this is the resource allocation graph and this is the corresponding wait graph here. So on the wait graph, okay, so P1, okay, P1 waits for P2, P2 waits for P4, and P4 for P1. Okay, so what can you conclude? You'll have here a loop here, and therefore this is a deadlock. So how do you write a code or a program to detect this? Okay, so several instances for resource type. So available, okay, allocation, and request. Okay, so available is a vector of length m, indicates the number of available resources for each type. The allocation, okay, the n by m matrix defines the number of resources for each type currently allocated to each process. Okay, and the request, an n times m matrix, indicates the current request of each process. So if request ij is equals to k, then process pi is requesting k more instances of resource type rj. Alright, so this is the detection algorithm here. So let work and finish be vectors of length m and n respectively. So initialize work equals available, just like what we did earlier in Banker's algorithm, alright, on the demonstration. So for I is equals to 1 to n, if allocation is not equal to 0, then set finish to false. Otherwise, finish is true. Okay, so find an index I such that both finish, okay, compared to false, and request I here is less than or equals to work. If no such I exists, you need to go to step number 4. Okay, here's the continuation. Okay, so work equals work plus allocation. Okay, so finish equals true. Go to step number 2. This is exactly the same thing that we did earlier. Okay, so if finish I equals false, for some I, 1 is less than or equals to I and less than or equals to n, then the system is in deadlock state. Okay, so moreover, if finish is false, then pi is in deadlock. Okay, so algorithm requires an order of O m times n squared operations to detect whether the system is in deadlock state. Okay, so this is in data structure, the big O notation. Alright, so let's have an example here of detection algorithm. Okay, so you are given here 5 processes, P0 to P4. Okay, 3 resource types, A, B, and C, 7, 2, and 6. Okay, so this is the snapshot at time 0. So if you will observe, so all the available resources were allocated. Okay, so from the detection algorithm, the sequence P0, P2, P3, P4, and P1 will result in finish I equals true for all I. Right? Now, what if P2 requests an additional instance of type 3? Okay, so take note that the available resources here could be 000, and you'll have P2 there requesting an instance of C. Okay, safety. Well, what is the state of the system here? Can reclaim resources held by P0, but sufficient resource to fulfill other processes requests. So deadlock exists consisting of process P1, P2, and P3 and P4 because they are requesting a resource. There are requests coming from P1, okay, P2, P3, and P4. Well, P0 don't have any requests. Okay, so deadlock exists consisting of process P1, P2, P3, and P4. Right? Next, detection algorithm usage. So when and how often to invoke depends on how often a deadlock is likely to occur, how many processes will need to be rolled back. So one for each disjoint cycle. So if detection algorithm is invoked arbitrarily, there may be many cycles in one resource graph, and so we would not be able to tell which of the many deadlock processes caused the deadlock. Okay, so recovery from deadlock, process termination. Okay, are we going to terminate the process and task to recover from deadlock? Well, abort all deadlock processes. Okay, abort one process at a time until the deadlock cycle is eliminated. So in which order should we choose to abort? So priority of the process, how long process has computed, and how much longer to completion. Resources the process has used, resources the process needs to complete, how many processes will need to be terminated, and is that process interactive or batch. Okay, so deadlock recovery. Once you've discovered deadlock, what you do about it is, well, abort one process to recover from circular wait. That process will likely have to start over from the scratch unless it is checkpointed. Okay, so which process should you choose? Well, of course, if you are in the work area, it's not your supervisor's process. All right, but if you are using your own computer, well, what we usually did is we just end the processes, end task on the task manager. All right, so recovery from deadlock, resource preemption, selecting a victim, minimize the cost, roll back, return to some safe state, restart process for that state, and starvation. Same process must always be picked up as victim. Include number of rollback in cost factor. So resource preemption is another solution. Okay, another solution is take resource away from the process. Again, which process should you use? How can you roll back that process to its state before it had a coveted resource? Make sure that you don't keep on preempting from the same process. Avoid starvation. That is what's being said here. All right. Okay, so combined approach for deadlock handling. So combine the three basic approaches: prevention, avoidance, and detection. Okay, so allowing the use of optimal approach for each resource in the system. Partition resources into hierarchically ordered classes. Use most appropriate technique for handling deadlocks within each class. Okay, so what are we going to do? Ignoring the deadlock. Perhaps not as silly as it sounds. All right. Use resource prioritization for heavily used resources. Otherwise, don't worry about it. The mechanisms outlined previously for handling deadlock may be very expensive, but if the alternate is to have a forced reboot once a year, that might be acceptable. Well, that's the claim of Microsoft, that their operating system is experiencing a single deadlock a year. Would you believe it? Well, that's it. Thank you for watching, guys. Have a good day.